Hello, I'm Adam Powell, an associate professor at Worcester Polytechnic Institute in Worcester, Massachusetts, New England's second largest city. WPI is home to the largest metal processing faculty in the United States. So my research group focuses on using metal process technologies for greenhouse emissions, reduction, elimination, and drawdown. In one project, a new silicon production process inspired by aluminum electrolysis cells could make solar silicon for just $2 per kilogram, using more than 90% less energy than the dominant Siemens process. In another, a new liquid metal anode direct carbon fuel cell achieves 65 to 70% efficiency in bioenergy with carbon capture, which is twice the efficiency of gasification plants with a much simpler flow sheet. Today, I will discuss a set of new clean energy projects we are working on, which relate to magnesium. Starting by acknowledging a long list of contributors that made possible the results showing today. So why magnesium? First, magnesium is a very energy-dense energy carrier with higher energy per unit volume than hydrocarbons and 5 times the energy per unit mass of iron. So much higher energy per unit volume than liquid hydrogen. Second, it is extremely abundant with 2 quadrillion tons in the oceans. That's 300,000 tons per human on the planet. Better still, we can produce it by making drinkable water by desalination. So we don't even need to dig to mine it. We just sit at the shore and magnesium comes to us. 1/1,000,000th of this, 300 kilograms per human, provides 1 month's worth of electricity for the average American, average US citizen, but enough for the entire planet at this rate. Third, magnesium is not only non-toxic, it is a necessary bodily nutrient with LB50 in rats measured at 4 grams per kilogram. So for a human, that would be about a pound of magnesium oxide. In contrast, silica and alumina are much more toxic, with aluminum linked to Alzheimer's disease, as of course are boron and beryllium. And in contrast, we drink magnesium oxide for upset stomach, and we dump magnesium chloride onto our roads by the hundreds of tons to melt ice. It's good stuff. And MgO also reacts with CO2, but I'm getting ahead of myself. So this is a layout of the overall vision. I'll walk through it and explain each part of it. We begin with seawater and use membrane desalination, as I mentioned, to produce fresh water. We take the remaining concentrate and react it with sodium hydroxide from the chloralkali process to precipitate out magnesium hydroxide, which we then dry and calcine to produce magnesium oxide. This is an existing industrial process that produced most of the magnesium used by the United States in World War II. The chloralkali process uses electrical energy, and in principle, drying and calcine can use electricity, resulting in 0 direct emissions. Existing desalination plants in service around the world today could provide enough seawater concentrate to produce 90 million tons of magnesium per year, which is about 100 times the present production. Next, we reduce magnesium oxide to metal in a 2-step process. First, we use a molten salt electrolysis with a reactive tin cathode, a liquid metal cathode, to reduce magnesium oxide to make a magnesium tin alloy. This is very similar to the Hall-Héroult process, which produces nearly all of today's aluminum. So an existing Hall-Héroult aluminum plant can be converted to magnesium production. Second, a new multiple effect distillation process separates this magnesium tin alloy to recover pure magnesium metal. This new magnesium metal distillation process is the key enabling technology for the whole ecosystem, so I'll spend more time on it in just a moment. We circulate the remaining tin with less magnesium back into the cathode of the electrolysis cell. This idea dates back to the 1940s, but it has never been economical because magnesium distillation has been an inefficient batch process with very long cycle time and high costs. When we think about it, distillation loses a lot of energy in the condenser. So vapor compression distillation recycles the condenser energy back into the evaporator. By itself, that's thermodynamically impossible, like a perpetual motion machine. But if we put energy in via a compressor, that raises the pressure of the condenser, which in turn raises the boiling point of the condenser above that of the evaporator. So the hotter condenser transfers heat to the cooler evaporator. This is so efficient that water vapor compression distillation can take as little as just 2% of the enthalpy of vaporization as input energy, with the other 98% coming from the condenser. That's for low salt water, not for seawater. So this is what we came up with. This is the rough scale of a 100 kilogram per hour pilot magnesium distiller. And here's what the inside looks like. It is a multiple effect distiller in which a single heater distills material in multiple evaporators and condensers called effects at decreasing pressures, effectively multiplying that heat's effect. Liquid magnesium flows from top to bottom. Liquid magnesium is the dark gray in here, with some of it evaporating off in each effect and the remainder flowing down to the next evaporator. So the condensers are shown here full of liquid magnesium until finally the concentrate with high solute concentration goes into the concentrate accumulator here at the bottom. The pressure difference and boiling point difference here is, in this process, is created by liquid height in these standpipes. So the lower evaporator and condenser are at higher pressure given by rho GH, density, gravity, and height, than the one above it, and therefore they transfer their heat upward. The energy use for even this 3-effect distiller is more than 90% lower than today's magnesium distillation processes and 60% lower than the vaporization enthalpy of magnesium. Even better, we can scale it just by making it wider to increase the surface area and production rate. And that larger distiller uses even less energy loses even less energy per the sides per unit production. Back to the reduction process, our first trials with molten salt electrolysis have achieved 97% current efficiency, that is Faraday conversion of current to magnesium metal. And our 1 and 2 effect batch distillation experiments to date have validated the heat transfer models, not just validated them, but nailed the predicted heat balance within 1 to 2%. This gives us confidence in our designs from the first continuous distillation experiments planned for this fall to our pilot and full-scale design studies. We can use magnesium metal alloys to reduce weight in motor vehicles. Magnesium density is just 1.7. That's considerably lower than aluminum. Holding a block of magnesium in your hand feels like holding a piece of wood. Magnesium-intensive auto body can be up to 60 to 70% lighter than steel, and even 20 to 30% lighter than aluminum. This shows the Ford and Magna multi-material lightweight vehicle, which was a design study in 2015, looking ahead 10 years to see what would be possible. And the full vehicle weight is 50% lower than the baseline, which is a 2013 Ford Fusion. So unlike composites, they chose magnesium alloys because magnesium can be stamped in traditional automotive production process. Magnesium is also fully recyclable using, of course, multiple effect magnesium distillation, as shown a moment ago. There are many barriers to widespread magnesium use, addressing primary production and recycling are two really important ones. The literature on alloy ductility and corrosion is vast, and I invite you to look at it. But my research group is making significant progress on these two and also on reducing corrosion in magnesium aluminum welds for these new vehicle bodies that take advantage of the best properties of both metals. Moving on, a criticism of wind turbines and hybrid electric and hydrogen vehicles is that they use rare earth permanent magnets in the motors, shown here as RE, or in the wind turbine generators. These magnets require neodymium, praseodymium, and dysprosium metals, which are currently produced using very dirty processes in China. There is currently no post-consumer rare earth magnet recycling. Liquid magnesium is a great leaching agent to recover the rare earth elements out of magnesium for recycling those magnets. But separating the rare earth magnesium alloy is a challenge. Once again, multiple effect distillation is usable to do this separation, and it reduces the overall flow sheet energy consumption by 70% and overall capital and operating costs by 50% compared with traditional vacuum distillation. Note, this is not meant to compete directly with magnet-to-magnet recycling like that of Urban Mining Company in San Marcos, Texas, which uses hydrogen to break the magnet down into individual grains and then resinter those grains into a magnet. Theirs is the simplest and most efficient magnet recycling method, but that process requires rare earth metal to make magnets comparable with in performance to new ones. This process uses much less energy than the electrolytic rare earth production in China, with 0 of the perfluorocarbon emissions, which are some of the most potent and persistent greenhouse gases. So, a new molten salt magnesium primary air battery can potentially deliver up to 125 megawatt hours from a 20-foot shipping container for ship and train propulsion. That's 40 times the energy of a containerized lithium iron battery at a tiny fraction of the storage cost per kilowatt hour. And of course, with 0 emissions in bringing 0 emissions to shipping. So the battery begins with a magnesium metal anode and a porous metal cathode, which delivers air into the cell. Magnesium from the anode and oxygen from the cathode become magnesium oxide dissolved in the molten salt. So that's the overall reaction of the battery, magnesium plus oxygen to magnesium oxide. Many of these can easily be stacked in a series as shown here for efficiency. The salt eutectic temperature and magnesium melting point bound the operating temperature between about 420 and 620 degrees Celsius. Here is a model of performance at scale showing operating voltage versus current density, with the orange curve showing power density. Because of the high reactivity of magnesium, the heat generated corresponds to 3.1 volts. It's 3.1 joules of energy per coulomb passed, and it can operate over a range of current densities which produce enough excess heat for the system. Starting at just 0.2 amps per square centimeter, it produces 0.5 watts per square centimeter at 80% efficiency. Or you can run at 7 times that power density at 2.6 amps per square centimeter. That's 3.5 watts per square centimeter, but at just 42% efficiency. So it has this wide range of operating conditions. Based on this, a 20-foot shipping container with a stack of 10 cells delivers up to 125 megawatt hours at 150 kilowatts for 600 to 800 hours of operation, enough to get a ship across the Pacific. So here's a plot of that same plot, but with actual voltage and current density measured from the first and third trials that we ever did for this system. The 1.9 volt open circuit voltage corresponds to 60% efficiency. And by the way, is the highest open circuit voltage ever achieved in a magnesium air battery, beating the prior record of 1.4 volts. The catch is that we cannot directly recharge these batteries. We need to disassemble them and return the magnesium oxide to the reduction plant for reduction back to magnesium metal. The plan is to use these to power ships for long voyages. For example, in a 20,000 container class vessel with a 60 megawatt engine, replacing 4% of the containers with these batteries is sufficient to power that 60 megawatts all the way across the Pacific. We can also ship magnesium battery anodes from countries where electric power is cheap to where it is expensive. And they carry 3.5 times the energy per unit weight of the best hydrogen shipping solution to date, which is a toluene methyl cyclohexane cycle, and require 0 platinum catalysts. We have cheap magnesium oxide input. We have a very cheap molten salts, which can be derived from seawater. This is off the charts performance for a battery due to the high voltage and low resistance of the molten salt and the absence of any passivation of the magnesium. There's no hydrogen to take energy away from the system. Indeed, it is comparable to hydrocarbons in energy per unit mass and much, much better in energy per unit volume. Next, this isn't our group's work, but a Massachusetts company called Safe Hydrogen is using magnesium, metal slurry, and mineral oil to store hydrogen for seasonal electricity storage. That is to store summer solar energy to use for winter heating. The 1 micron slurry is pumpable and stable. You can drop a lit match into it or even hit it with a blowtorch and it won't ignite because the mineral oil protects the magnesium by providing a reducing environment. They can hydride and dehydride the slurries, go from a magnesium metal powder to hydride powder just by changing the pressure, so with little round-trip energy loss. The economics may or may not be competitive with long-term batteries such as Form Energy, but the cost per kilowatt hour is very low, and it's not clear how the round-trip energy efficiencies compare. That said, for industrial technologies such as hydrogen direct reduced iron steelmaking by the hybrid process, this magnesium-based solution is likely the best method for intermediating between hydrogen production when intermittent renewables are cheap and consumption on demand when needed by the industrial process, including seasonal storage of hydrogen. Finally, we come to aviation fuel. Inspired in part by Safe Hydrogen, my group is working with WPI professor Jagan Jayachandran in aerospace to use a similar magnesium hydride slurry as a zero emissions jet fuel. The exhaust consists of CO2, water, and magnesium oxide nanoparticles. These particles react with combustion CO2 or atmospheric CO2 to remove it from the atmosphere as dilute magnesium carbonate or bicarbonate rain. This effectively accomplishes aircraft propulsion and CO2 capture and sequestration all in a single operation, sequestration in the oceans. With biofuel hydrocarbon, it is net negative CO2. Using an open source combustion thermodynamics program called Cantera from the MIT Laboratory for Aviation and the Environment, we've calculated the adiabatic flame temperature versus ratio of fuel to stoichiometry with air. An equivalence ratio of 1 corresponds to a stoichiometric combination of carbon or magnesium plus oxygen to CO2 and MgO and carbon or magnesium hydride with the hydrogen forming water. Therefore, these jet engines generally burn a lean, and an equivalence ratio less than 1 shows how much leaner. As you can see, slurries with high magnesium hydride loading burn at a higher adiabatic temperature because magnesium is a better energy carrier. What's important here is how much fuel is needed to reach a certain temperature, because that determines the thrust. So per unit mass, it takes a higher mass of this slurry, the 65% slurry corresponding to a 1-to-1 magnesium to carbon ratio than for your hydrocarbon. That said, if we look at a comparison between the lower heating values, that does not tell the whole story because magnesium combustion is a few percent more efficient because magnesium oxide is more stable at the higher temperature, whereas carbon dioxide and water would decompose into carbon monoxide, hydrogen, and oxygen. So the actual mass ratio shown in these triangles is considerably lower than the mass ratio that you would predict just from the lower heating value energy densities of the metals. If we look at the volume ratio, it takes substantially less volume, as mentioned, to achieve the same amount of energy. Again, with the actual values being lower than what you predict for the using the lower heating values. Now, this effect is especially pronounced at higher temperatures, but those temperatures are somewhat higher than today's materials can achieve. So I jumped the gun with the punchline, which is that based on the higher energy density per unit volume and higher efficiency, the Breguet aircraft range equation, which takes into account the volume and mass energy density, shows a 6 to 8% longer range for this fuel than Jet A or a simple hydrocarbon surrogate such as dodecane shown here. By comparison, filling the same tanks with liquid hydrogen or ammonia achieves only 30 to 40% of that range at comparable efficiency to the hydrocarbon fuel. We believe that this is the only greenhouse gas-free aircraft propulsion solution with flight range at least as long as hydrocarbon fuels. In summary, magnesium is a safe, abundant, high energy density, and flexible energy storage material. It can potentially deliver carbon neutral energy with best-in-class, no compromises performance for many applications, particularly for aviation, ship propulsion, energy shipping, hydrogen storage, lightweight vehicles, rare earth magnet recycling, with everything powered by renewable electricity. We have a long way to go before this metal with low production today can begin to fulfill its potential in these roles. But I hope I've shown you the extraordinary ability of magnesium to act as a clean energy alternative, which can potentially disrupt our carbon energy system. Let me thank our sponsors and collaborators and all of you for joining me. I look forward to our discussion during the conference.